Hi, welcome back. In this video, we are going to be talking about inference with paired means or paired samples. Paired T procedures are mechanically going to be the same as our one sample T procedures. The setup is going to be a little bit different, but the actual process, the mechanics of the test are going to be different. The key thing is that we are going to be starting with matched paired data. So we will have two samples, but unlike our last test of the independent two sample T procedures, we have data that is not independent, it's actually matched pair. So our big kind of tricky thing is going to be figuring out when we should use this procedure. So with a paired means t-test, our parameter of interest is going to be mu sub d, or the true population mean difference between these two situations. The data that we are going to collect is we are going to have two data sets, x1 and x2, and this will be paired data. So this could be paired data like before and after. This could be paired data by geographic location, but it's paired data. And we are going to calculate D, which will be a difference, which we will write as x1 minus x2. So this is a pairwise difference. And we are going to have a sample size, which will be n sub d, which is the number of differences. With paired means, our assumptions and conditions that we need to check are going to be very similar for the most part, but our first assumption and condition is different from anything we've done so far. And that is that we must have paired data. And with this paired data, we want to identify how it is paired. So this means we do not have independent samples. These samples are paired. It could be paired by person. It could be paired by location. It could be paired by couple. But we want to identify how the data is paired to make sure that we know it is not independent. Then we need independence for our observations. Are the differences reasonably independent? So here we are looking at we are looking at the individual observations in x1 independent of each other and the individual observations in x2, but we're really looking at these differences because they're paired data. All of the independence and our nearly normal check are going to relate to the differences. So do we have a random, or do we have random or a representative sample of differences? And then we are looking at the less than 10% of population if sampling without replacement. And the last criteria, the sample size, is checking nearly normal for our differences. And it's really important here. We are not checking the distribution of x1 and x2. We are checking the histogram. We are checking normality for our differences. So we are looking for our population of differences to be approximately normal. This means we are going to look at a histogram of differences And the main things that we're looking for is that we're looking for it to be approximately mound-shaped, approximately symmetrical, and no outliers. The no outliers is the really important one. If we have outliers, we really need to take that into consideration, and we are possibly going to need to make some adjustments, but we are looking for there to be no outliers. If we don't have that met and our sample size is larger than 30, that's going to tend to be okay. But we really, even if we have a sample size larger than 30, if you have the data set, we want to look at the histogram, and we are especially checking to make sure we have no outliers. We are going to be doing inference for confidence intervals as well as histograms. I'm going to go kind of fast because this is not our first test. So for a confidence interval, this is going to be a best estimate plus or minus a margin of error. Our best estimate is going to be D bar, which is the mean of sample differences. So we need to get the differences and then average those. And our margin of error is going to be a critical value multiplied by a standard error. In this case, that will be a T star times a standard error. Our critical value is going to be the same as it has been so far. Our degrees of freedom will be n sub d, so our number of differences minus 1. So we are going to be looking at n sub d as our number of differences, and our degrees of freedom is n sub d minus 1. Our standard deviation or standard error, we are going to be looking at standard error here because I don't know the true population standard deviation. Our standard error is going to be the sample standard deviation of differences divided by the square root of the number of differences. And again, the standard deviation is always of a sample is always going to be an underestimate of the population. So that's why we're going to use the t-distribution. So for our confidence interval, our best estimate is going to be D bar plus or minus a T star critical value based on the number of differences minus 1 times the standard error. For our hypothesis test, our null hypothesis is going to be that the mean difference is equal to some assumed true mean difference. And our alternative is going to be that the true mean difference is less than, greater than, or not equal to that assumed truth. Our test statistic is going to be a t. So t sub t is equal to d bar minus, so our sample mean minus our assumed truth divided by our standard error, which is the same thing that it was for confidence interval, which is SD over the square root of ND. And we are going to find our p-value just like we did with a one sample, which is for a left tail, we're looking at just the area to the left of T star. If it was a right tail, we would be looking just at the area to the right. And for a two tail, we need to look at the negative and the positive and look at the areas on either side of that. And we will use a TCDF to do that. In the next two videos, we're going to look, or in the next three videos, we're going to look at an example, checking assumptions, hypothesis test, and confidence interval.